Welcome back to the channel. Thank you so much for joining us for another journey through Earth's deep past. If you enjoy this kind of science storytelling, please remember to like the video, subscribe, and share it with someone who loves mysteries about our planet. It really helps the channel grow. I am also curious about you. What time of day are you watching or listening to this? And where in the world are you right now? Let me know in the comments below. Now let's begin. In the tropical heat of a Madagascan afternoon, the forest canopy throws a patchy shade over a small expedition, forcing its way through dense growth. Legs push through underbrush of wild banana, mango and palm, and metal flashes now and then as machetes clear a narrow path. The year is 1860, and for the group of European naturalists following their local guides, these inland forests are in their view unexplored country. Behind them lies the sea, and beyond that the familiar outlines of Africa. Around them stands a living world that does not match what they know from those coasts. Trunks swell into bloated baobabs, orchid flowers cling to moist bark, and calls erupt from the branches overhead in unfamiliar patterns. Among those branches move lemurs, small primates with large eyes, long limbs and tails held out for balance as they cross gaps in the canopy. A striped tail appears briefly in a shaft of light black and white bands, swinging as the animal leaps away from the noise of the party below. The scientists in the undergrowth do not see the whole animal, but one of them notes the pattern quickly in his damp notebook. For him, it is one more variety to add to an expanding list. Crates of dried plants and preserved skins wait on the coast ready to be shipped to Europe. When the season turns, those crates and that notebook will cross the ocean and enter a different setting, the cabinet rooms and lecture halls of Victorian science. Months later, in a cool office far from the tropics, a zoologist studies the contents of those crates. He spreads specimens and sketches across a table, handling each labelled skin and skeleton with care. He's already made a reputation in the study of birds and their global patterns, but the lemurs from Madagascar demand a different attention. There are many forms. Some are small and slender, others are stocky with thick fur, some carry ringed tails, some show distinct patches of colour around the face and limbs. Compared with the limited lemur fauna known from Africa and from the Indian subcontinent, the range of types on this single island is striking. The zoologist counts several dozen distinct species, all adapted to forest life, all clearly related, and yet they are restricted to one patch of land separated by ocean from the nearest mainland. He knows that ocean water is a barrier for most land mammals. He also knows that some animal groups have wide distributions that span oceans. Somewhere there must be a common explanation for these patterns. At this point in the 19th century, earth sciences and biology are in transition. Geologists debate whether continents can rise and fall on a global scale. Some imagine vast areas of land slowly sinking beneath the sea to create deep ocean basins, while other land is pushed up in compensation. Naturalists confronted with similar or related species on opposite sides of an ocean often invoke land bridges that once connected now distant coasts. It seems a straightforward solution. Land animals could cross plants, could spread, then the land bridge could sink or be broken, leaving separated populations to change in different directions. In this way, lost continents become a working tool in early studies of how life is spread across the planet. The zoologist examining the Madagascan lemurs leans on such ideas. If Madagascar holds such a rich and varied lemur fauna, while Africa and India hold only a handful of species, then perhaps the island is the original homeland of the group. From there, in his reconstruction, lemur ancestors reach the neighbouring regions over a broad lowland that no longer exists. He imagines a landmass that once filled much of what is now the western Indian Ocean, connecting Madagascar to Africa on one side and to India on the other. The lemurs in this view roam across this large region, spreading into new forests as climates shift and rivers change course. When the land sinks or is gradually submerged, only the higher parts remain above sea level. Madagascar survives as an island remnant of a former continent. India and Africa remain as larger fragments at the edges. The zoologist gives a name to this imagined lost continent, building it from the word lemur and the long tradition of classical naming. For his contemporaries, this is not fantasy, but a serious scientific proposal. The existence of such a landmass seems to solve an immediate puzzle in the distribution of primates and to fit with broader geological notions of subsiding continents and rising sea floors. As the idea circulates, other thinkers adopt and modify it. In the later decades of the century, debates around the evolution of humans are intense. Some scholars argue for an African origin, others for an Asian cradle. In this environment, the proposed lost continent acquires a new role. A few writers suggest that not only lemurs but also early human ancestors may have arisen there in some intermediate region between Africa and Asia. Maps in popular work show a broad tongue of land in the Indian Ocean, labelled in hopeful terms as an ideal early homeland, the first home of humankind before a catastrophic sinking. The boundary between formal science and speculation is permeable in this period, and the imagined continent moves back and forth across it. Spiritual movements of the time also draw on the language of hidden lands and vanished worlds. The lost continent named for lemurs is taken up in esoteric writings as the home of a former human race, with unusual bodies and abilities living alongside now extinct reptiles, and meeting an eventual destruction in fire and flood. In these accounts, geography and geology become backdrops for spiritual narratives. The original zoological reasoning based on the uneven distribution of lemurs and the need for past connections between land masses fades from view. Yet the central notion of a drowned continent lingers in the wider culture well into the 20th century. It appears in adventure stories, in mystical diagrams, and in speculative histories that place hidden knowledge in sunken lands. As scientific methods improve, the lost lemur continent faces increasing pressure. Marine surveys begin to measure the depth and structure of the ocean floor. Seismology and early geophysics reveal that the crust beneath the Indian Ocean has a different character from continental crust. It is thinner, denser, and made largely of basaltic rock produced at mid-ocean ridges, not the thicker granitic crust that underlies true continents. No sign appears of a vast plateau of sunken continental rock stretching between Madagascar, India, and Africa. At the same time, studies of current storms and rare events show that even land mammals can, under unusual circumstances, cross sea gaps on floating mats of vegetation torn from river banks or coastal forests. Over long periods of time, such rare crossings can explain some puzzling distributions without needing a whole missing landmass. The development of the theory of plate tectonics in the middle of the 20th century finally removes the need for most lost continents. Continents are recognized as relatively rigid plates of buoyant crust that move slowly across the surface of the planet, carried by currents in the underlying mantle. Ocean basins are seen not as former continents that have sunk wholesale, but as areas where new crust is created and spreads outward from ridges, while older oceanic crust is pushed down into subduction zones. With this framework, the puzzle of Madagascar and its lemurs is rephrased. Madagascar, India, and Africa once formed part of a single supercontinent, later named Gondwana. As that supercontinent breaks apart, Madagascar and India drift away together, and then separate while Africa follows its own path. The lemurs in this view evolve on land that is at times continuous, and at times broken into islands without requiring any additional vanished continent beyond the already complex story of Gondwana. The imagined continent named for lemurs does not disappear entirely. Instead, it changes category. It moves from a serious scientific hypothesis to a historical example of how scientists once tried to make sense of limited data. It becomes a cautionary story about stretching a single line of evidence too far when the broader physical context is still unclear. At the same time, the path of the idea from scientific proposal to spiritual symbol illustrates how concepts about Earth's deep past can take on lives of their own outside the scientific community. In this way, the story of the lost lemur land forms an entry point into a larger question. If one invented continent can so strongly capture imaginations, what happens when real ancient continents assembled and broken apart by plate tectonics are traced through rocks, fossils, and magnetic records? The answer leads towards supercontinents, worlds where most or all of the land on Earth is joined, and toward the question that underlies this whole narrative, how those repeated unions and breakups of land have shaped the history of life, and what they might mean for its future on this planet. Towards the end of the 20th century, another small expedition approaches a very different world. This time there is no forest, no heavy air, no lemurs calling from the trees. A spacecraft built on Earth falls inward toward Venus, a planet similar in size and mass to Earth, but hidden beneath an opaque layer of clouds. The probe is part of a mission named Magellan launched by a national space agency to map the surface of Venus with instruments that can see through the clouds. After several years in orbit sending back data pass after pass, the spacecraft is finally commanded to descend into the atmosphere. Its body heats and breaks apart and its signal fades. By then its main work is long complete. Magellan has circled Venus thousands of times in a near-polar orbit, passing from north to south and back again, allowing the slowly rotating planet to turn beneath it. On each pass, the spacecraft sends out pulses of radio waves and listens for the echoes. This technique, known as radar, allows it to build up images of the surface by measuring the strength and timing of the returning signals. Over the course of a few years, Magellan maps almost the entire solid surface of Venus at a resolution that makes volcanic structures, fracture zones, and broad plains clearly visible. When these radar images are assembled into global mosaics, a striking picture emerges. Venus shows mountains, rifts, and chains of volcanoes, but it does not show anything like the continents familiar from Earth. There are no wide plateaus of thick, buoyant crust standing high above global average level, no broad regions of mixed rock types, analogous to Earth's old continental cores. Instead, Venus is dominated by vast basaltic plains. Basalt is a dark volcanic rock that on Earth forms much of the ocean floor. On Venus, similar material appears to cover almost the entire surface, broken by ridged belts, folded highlands, and scattered volcanic rises. There are high regions, some with complex patterns of fractures and faults, but they lack many of the clear signatures of stable continents that have floated and collided for billions of years. For scientists studying planetary geology, this difference is very important. Earth and Venus begin with similar bulk properties, yet their outer shells behave in fundamentally different ways. Earth shows plate tectonics, the slow but persistent movement of rigid plates of lithosphere that carry continents and ocean basins across the globe. Plate boundaries concentrate earthquakes, build volcanic arcs, and raise mountain chains. Continents grow when buoyant crust is thickened and refined at these boundaries. In contrast, the Magellan data and later analyses indicate that Venus has what is sometimes called a stagnant lid. Its outer shell appears to be a single continuous plate, with no long-lived system of spreading ridges and subduction zones like those on Earth. Deformation is distributed in belts and clusters, but there is little evidence for large plates sliding past one another or sinking wholesale into the interior. Without this kind of lateral motion and recycling, it is much harder to generate and maintain the differentiated crust that stands out as continents. The radar images of Venus also suggest a different style of surface renewal. On Earth, new crust is produced continually at mid-ocean ridges and consumed at trenches. The age of ocean floor increases with distance from the ridges, and continents carry fragments of very old crust. On Venus, the crater record and the arrangement of volcanic plains suggest that large parts of the surface may have been resurfaced relatively rapidly in one or a few global episodes when massive outpourings of lava and widespread deformation overprinted older landscapes. After such an event, the surface might sit quietly for a long period with little localized plate motion. This pattern, if correct, implies a planet whose surface history is marked by long plateaus of relative stability, interrupted by catastrophic change rather than by continuous slow drift. The contrast raises a fundamental question. Why does Earth sustain mobile plates and long-lived continents, while Venus of similar size does not? Several factors are likely to play a role. Water in the mantle and crust can weaken rocks and promote the kind of faulting and subduction needed for plate tectonics to operate. Earth holds large amounts of water both at the surface and stored in minerals. Venus appears extremely dry. Its surface pressure is high, and its atmosphere is full of carbon dioxide and sulfur compounds, but the measured levels of water vapor are low, and chemical signatures point to a past in which whatever surface water Venus once had was largely lost to space or bound in reactions. This dryness may make its lithosphere stronger and more resistant to breaking into plates. Internal heat flow is another factor. Both planets started hot, but their cooling paths may have diverged. If Venus retains heat more efficiently under its thick insulating atmosphere, its mantle may favor episodic overturns rather than slower focused convection cells that align with plate motions. The absence of a strong global magnetic field on Venus in contrast to Earth hints at differences in core dynamics that might also couple back to mantle behavior over long timescales. These are working ideas rather than settled answers. For the present narrative, the most important point is that Earth's continents and supercontinents depend on a specific tectonic mode that is not guaranteed on all rocky planets. In the context of planetary climate, this difference has consequences that reach beyond geology. Earth's mobile plates participate in a long-term feedback known as the carbon-silicate cycle. Carbon dioxide is released by volcanoes and by metamorphic reactions in subduction zones. Over time, that gas dissolves in rainwater, reacts with rocks on land, and is carried by rivers to the oceans where it can be locked into carbonate minerals. When ocean floor bearing those minerals is subducted, carbon is transported back into the mantle. This loop operates over millions of years and helps keep Earth's climate within a range that allows liquid water at the surface. Continents uplifted by collisions and mountain building present large reactive surfaces to rainfall and glacial erosion, accelerating the weathering step of this cycle. Their distribution also guides where oceans and storm tracks focus. Venus, lacking stable continents and long-lived plate boundaries, appears not to run the same kind of global thermostat. Its thick carbon dioxide atmosphere traps heat efficiently, leading to surface temperatures hot enough to melt lead and pressures dozens of times higher than those at sea level on Earth. Any water once present at the surface would have been driven into the atmosphere and then dissociated by high-energy sunlight, with the lighter hydrogen escaping to space. Once this process runs to completion, the planet is left dry with no easy way back to moderate conditions. Without plate tectonics to pull carbon from the atmosphere and bury it deep for long periods, there is no strong sink to counter volcanic sources. In this way, Venus stands as a nearby example of what a world of Earth's scale can become without drifting plates and rising continents. The comparison is not used here as a warning, but as a scientific control. One planet Earth follows a path with surface recycling supercontinents and a complex rock cycle. The other follows a different path with the stagnant lid basaltic plains and an extreme greenhouse atmosphere. The reasons for this divergence are still studied with computer models and laboratory experiments, and new missions are being planned to return to Venus with improved instruments. Each new measurement, each subtle variation in topography or gravity, adds another piece to the puzzle of how planetary interiors and surfaces co-evolve. For those thinking about supercontinents, the lesson from Venus is simple in outline but rich in implications. Supercontinents are not just large clusters of land. They are expressions of a particular style of deep planetary motion, one in which plates split, move, and collide over billions of years. Without that motion, no Gondwana and no Pangaea would ever have formed. Continents might still exist as thickened patches of crust, but they would behave differently, and the long rhythmic gathering and dispersal that shapes Earth's biological and climatic history would be absent. When scientists look out at rocky exoplanets orbiting other stars, they must therefore ask not only whether those worlds lie at the right distance for liquid water, but also whether their interiors, compositions, and thermal histories allow anything like Earth's tectonic regime. At present, direct answers are out of reach. Only on Earth and Venus are the surfaces known well enough to compare. Yet by studying the difference between a world with continents and a world without them, researchers begin to outline the range of possible planetary behaviours. In that range, Earth's supercontinents are a special case, not an automatic outcome. The maps produced from Magellan's radar echoes thus do more than reveal the face of a hidden planet. They mark the boundary of a question that will recur throughout this story. How rare is the combination of processes that gives a planet-wide drifting continents and the ability to build supercontinents again and again, and how deeply has that combination shaped the path of life on Earth? On Earth, the difference between continental and oceanic crust begins with how each type is made and how long it survives. Oceanic crust forms where plates move apart along mid-ocean ridges. Their hot mantle rocks rise, partially melt, and feed chains of underwater volcanoes. The lavas that cool from these melts are rich in iron and magnesium and form dark basalt, a relatively dense rock. This new ocean floor moves away from the ridge as more material is added, and in time it meets a plate boundary where it can be forced back down into the mantle. In this way, most oceanic crust is created, carried, and destroyed on timescales of a few 100 million years. Continental crust follows a slower and more complicated path. It tends to be thicker and less dense than the basaltic crust of the oceans, with a composition closer to granites and related rocks that contain more silica and light elements. This composition is not present from the start. Instead, continental crust is gradually extracted and refined from mantle material and from older crust through repeated episodes of melting, mixing, and crystallization. Subduction zones where one plate is pushed beneath another play a central role. As the downgoing oceanic crust sinks and warms, water and other volatiles are released from its minerals into the overlying mantle wedge. This addition lowers the melting point of the mantle rocks, producing magmas that rise toward the surface. Some magmas erupt as chains of volcanoes, but a large fraction stalls and cools slowly within the crust. During this cooling, crystals form and settle, changing the composition of the remaining melt. Heavy minerals rich in iron and magnesium separate first, leaving behind melts that are lighter and richer in silica. These evolved magmas may eventually produce granite-like rocks that add to the continental mass. Over long periods, repeated cycles of subduction, arc magmatism, and continental collision build up thickened belts of crust, which then stand higher than surrounding regions. These belts are further modified by heating at depth, by underplating of magmas from below, and by partial melting during mountain building. The result is a complex layered structure in which ancient rocks can be preserved deep within younger terrains. Because continental crust is buoyant compared with the underlying mantle, it resists being driven back down to great depth. Portions can be buried and later exhumed, and blocks can be broken apart and rearranged, but once formed continental material tends to survive in some form. This property allows fragments of very old crust to remain at the surface for billions of years, even as the global pattern of plates changes. To trace this deep history, geologists turn to minerals that can record both age and origin. Among these, zircon occupies a special place. Zircon is a small, durable crystal of zirconium silicate that forms in many types of magma, particularly in those that are relatively evolved. It incorporates uranium atoms into its lattice when it grows, but excludes lead. Over time, the uranium decays into lead at a known rate. By measuring the ratios of uranium to lead in a zircon and comparing them with the known decay constants, scientists can calculate when the crystal formed. Because zircon is resistant to weathering and high-temperature alteration, it often survives even when the rock that first hosted it is eroded away or transformed. Grains weather out are carried by rivers and deposited in new sediments where they can be buried lithified and later exposed again. Each zircon grain thus carries a timestamp from its original crystallization, as well as chemical signatures that reflect the composition of the magma from which it grew. Over the past decades, laboratories around the world have dated many tens of thousands of zircon grains from rocks on all continents. When these ages are plotted, patterns emerge. The distribution is not uniform through time. There are clusters or peaks where many zircons record similar ages and troughs where relatively few ages fall. At first glance, one might expect zircon production simply to increase as more crust accumulates, or to vary only gradually with global conditions. The presence of pronounced peaks suggests that there are periods when the processes that create zircon-bearing magmas are especially active. These peaks appear to correlate with times when major continental collisions and supercontinent assemblies are thought to have occurred. For example, many zircons have ages that fall around times associated with the assembly of supercontinents known as Columbia, Rodinia, Gondwana, and Pangaea. In these intervals, wide belts of crust were being thickened, melted, and reworked as continents converged. This environment is favorable for generating large volumes of evolved magmas and thus for forming abundant zircon. Between these peaks lie intervals where fewer young zircons appear in the record. These gaps do not mean that no magmas formed, or that no crust was added. Instead, they may indicate changes in the dominant tectonic regime. During long stable periods when supercontinents remain assembled, plate motions can slow, and subduction zones can become less extensive or more widely spaced. New crust may still form, but perhaps in smaller volumes or in settings less conducive to zircon production. Alternatively, erosion and later recycling may preferentially destroy or bury rocks from some intervals, leaving a biased sample at the surface today. Distinguishing between these possibilities is an active area of research. Chemical analyses add another layer of information. By measuring trace elements and isotopes within zircon grains, geologists can infer aspects of the source rocks and the degree of crustal reworking involved. Some zircons show signatures that point to direct derivation from mantle melts. Others indicate that their magmas melted older continental crust. When these data are combined with ages, they suggest that Earth's crust has passed through stages. Early on, during the Archean Eon, much crust seems to have formed rapidly from mantle sources, followed by episodes of recycling and purification into more evolved continental compositions. Later, during the Proterozoic and Phanerozoic eons, reworking of existing crust plays a larger role. The zircon record thus acts not only as a calendar, but also as a tracer of how continental material is made and remade. Yet even with these tools, puzzles remain. Some of the oldest zircons, more than 4 billion years in age, are found as detrital grains in younger sedimentary rocks in regions like Western Australia. Their chemistry implies that by the time they crystallized, Earth already had continental-type crust and perhaps even surface water. However, almost no intact rocks from that early time survive. The crust that hosted those first zircons has been recycled or deeply altered beyond recognition. The presence of these ancient grains raises questions about when plate tectonics in a recognizably modern form began. Did Earth's surface operate under a different tectonic style for its first few 100 million years, with short-lived crustal plates or local overturns, before settling into the long supercontinent cycles recorded later? Or did something like plate tectonics start early, but its initial products were too thin or too fragile to resist destruction? The clustering of zircon ages at later times poses related questions. If zircon peaks coincide with supercontinent assembly, does that mean that Earth's interior rhythm, the pattern of mantle convection that drives plate motions, naturally leads to repeated cycles with roughly similar periods? Some studies suggest that the spacing between supercontinents, judged from geological reconstructions and from zircon data, falls in a broad range of hundreds of millions of years. This could reflect characteristic scales of convection cells in the mantle set by planetary size and material properties. However, the record is noisy, and each proposed supercontinent has uncertainties in timing and extent. It is also possible that some peaks arise from several regional events, overlapping in time rather than from a single global assembly. The zircon record is therefore both a guide and a source of ambiguity. It confirms that crustal growth is not steady. It ties episodes of intense magmatism to known or suspected collision events. At the same time, its gaps and uneven sampling leave room for different interpretations of how continuous or episodic Earth's tectonic engine has been. For the story of supercontinents, this matters because it bears on how predictable the cycle of gathering and dispersal might be. If there is a strong underlying rhythm, then supercontinents might be seen as expressions of a deep planetary heartbeat. If the pattern is more irregular, with some intervals dominated by incomplete assemblies or staggered collisions, then each supercontinent is a partly contingent outcome of complex flows in the mantle. In both cases, the making and unmaking of crust tracked through tiny resilient crystals is central to understanding how Earth alone among the inner planets holds a surface where continents not only exist, but repeatedly come together to shape the conditions for life. Earth's surface today presents a patchwork of continents and oceans, yet within that present pattern lie traces of past arrangements. The first hints come from something as simple as the shapes of coastlines. Along the western edge of Africa and the eastern margin of South America, the outlines seem to complement each other. Early cartographers noticed this, but for centuries it remains a curiosity. As maps improve, the fit becomes sharper. Not only do the gross shapes of continents suggest former proximity, but particular shelves and ridges on the submerged continental margins appear to align if the Atlantic is closed. In the early 20th century, A meteorologist named Alfred Wegener gathers these observations and proposes that continents drift. He points to the geometric fit of South America against Africa of North America, against Northwest Africa and Europe, and argues that these pieces once formed part of a single larger landmass. He notes that similar rock formations and mountain belts appear on both sides of the Atlantic. Layers of rock in eastern North America match those in Scotland and Scandinavia. Folded belts in Brazil align with those in West Africa. When imagined together, they form continuous chains that are now broken by the ocean, but would reconnect if the continents were pushed back together. This pattern suggests that mountains do not arise randomly. They tend to form along the seams of former collisions, and when those seams are split, their halves drift apart and carry echoed structures to distant shores. Fossils provide another line of evidence. On several southern continents, including South America, Africa, India, Australia, and Antarctica, geologists find remains of the same fern-like plant named Glossopteris. These fossils are held in ancient coal-bearing rocks that indicate similar swampy conditions. The distribution is hard to explain if the continents have always been where they are now, separated by wide and deep oceans. It becomes easier to understand if those landmasses were once joined in a single southern supercontinent, where the plant spread freely before later breakup carried its descendants to different parts of the globe. In other cases, small reptiles such as Mesosaurus occur only in rocks of South America and Africa, again pointing to former land connections because it seems unlikely that such animals could cross broad ocean basins. The patterns are not perfect. Some fossil groups have surprisingly wide ranges despite the apparent absence of connections, while others are restricted to narrow areas even when land links seem to have existed. These mismatches hint that the story involves more than simple geography. Climate, ecological barriers, and the timing of evolution all play roles, and they complicate efforts to read a single clean history from species alone. Still, when fossils, rock units, and coastline shapes are considered together, a consistent picture of past continental unions emerges for many parts of the world. A third major line of evidence comes from the magnetic properties of rocks. When volcanic rocks cool or some sedimentary rocks form magnetic minerals within them, align with the prevailing direction of Earth's magnetic field. This field has a north and south pole. Over long intervals, the poles wander around the globe as the axis of the magnetic dipole shifts relative to the spin axis. At irregular times, the polarity also reverses so that what is now north becomes south, and vice versa. These features create a complex but decipherable pattern in the magnetization of rocks of different ages. When geophysicists measure this magnetization carefully, they can determine the direction and inclination of the magnetic field at the time the rock formed. From this, they can infer the latitude at which the rock cooled or was deposited. If a sequence of rocks from a single continent shows a systematic change in inferred paleolatitude through time, it likely means that the continent has drifted northward or southward. When the paths derived from different continents are compared, they often do not match if the continents are held fixed in their modern positions. However, if the continents are rotated and translated relative to one another, the paths can be brought into agreement. This process allows scientists to reconstruct how the continents must have moved with respect to the magnetic poles and to each other. In the ocean basins, magnetic measurements provide even more direct information about past plate motions. As basaltic lavas erupt along mid-ocean ridges and cool, they lock in the current magnetic polarity. Because the global magnetic field reverses at irregular intervals, this creates a pattern of stripes of normal and reversed polarity in the ocean crust, symmetrically arranged on either side of the ridge. When research vessels tow magnetometers across the seafloor, they record these stripes as linear anomalies in field strength. On a map, the pattern resembles a barcode. By matching the sequence of stripes with the known chronology of magnetic reversals derived from continental rocks, geophysicists can assign ages to different parts of the seafloor. They find that the youngest rocks lie along the ridges, and that age increases symmetrically away from them. The oldest oceanic crust preserved is on the order of a few 100 million years old, much younger than the oldest continental rocks. This age limit reflects the cycle of creation and destruction of ocean crust at spreading centers and subduction zones. By combining ridge age patterns with known plate boundaries, scientists can reconstruct how oceans have opened and closed. The Atlantic, for instance, appears young. Its floor becomes older away from the central ridge toward the coasts, but nowhere approaches the billions of years recorded in continental crust. This shows that the Atlantic has not always existed. Before it opened, the continents on either side must have been joined. The seafloor magnetic record thus anchors the more qualitative suggestions from coastlines and fossils with quantitative timing. Mountain belts carry yet another kind of record. When two buoyant continental blocks converge, neither can easily sink. Instead, the crust between them thickens, shortens, and rises, forming ranges like the Himalaya and Tibetan Plateau today. Deep within these ranges, rocks are pushed to high pressures, and temperatures then later uplifted and eroded, bringing their deformed interiors to the surface. These rocks preserve structures such as folds, thrust faults, and metamorphic mineral assemblages that reveal the conditions during collision. By mapping the orientation and extent of such belts, geologists can identify ancient collision zones now exposed as orogenic belts on every continent. Many of these belts can be traced across present-day ocean gaps by matching rock types, deformation styles, and isotopic signatures. For example, a belt running through eastern North America lines up with one in Western Europe and another in Northwest Africa, forming a continuous curve when the Atlantic is closed. The same is true for belts around the margins of the Indian Ocean. Through this network of scars, the outlines of former supercontinents become clearer. Yet, as with other evidence, there is room for disagreement. In some regions, the belts are overprinted by later events, making their original roles hard to determine. Multiple collisions can occur along the same general line over time, complicating the record. Some crustal blocks may have rotated independently, changing the orientation of structures relative to global coordinates. Piecing together the jigsaw requires choices about which features to align and how to weigh different lines of evidence. As a result, reconstructions of supercontinents such as Rodinia show significant variation between research groups. In some models, certain cratons from what are now China and Siberia lie adjacent to Western North America. In others, they occupy quite different positions. The timing of assembly and breakup can also vary by tens of millions of years between models. These discrepancies do not mean that the overall concept of past supercontinents is in doubt. There is broad agreement that there have been times when most of Earth's land was gathered into a few large clusters, and that these broke apart to form new configurations. But the precise details of each configuration and the exact paths taken by individual blocks remain partly unresolved. This situation introduces a subtle kind of mystery. The Earth's surface is physical and continuous, yet our reconstructions of its past states remain blurred at the edges. Each new dataset, whether from a previously unsampled mountain belt, a refined magnetic measurement, or a newly dated volcanic suite, can shift a crustal fragment by hundreds of kilometers in a reconstruction. That shift can alter paleogeographic maps, changing where coastlines lie, where ocean currents flow, and where mountain ranges stand. In turn, this changes inferred climate patterns and the pathways available to land and marine life. These scars of drift are therefore not only records of plate motion, but also boundaries on our understanding. They show that continents have come together and moved apart many times, that oceans have opened and closed, and that supercontinents have existed. At the same time, the partial and overlapping nature of the evidence leaves open multiple plausible histories within the constraints. For the purposes of this narrative, the key point is that supercontinents are not single, perfectly known maps in a textbook sense. They are best viewed as ranges of likely configurations constrained by rocks, fossils, and fields. Within those ranges, different placements of blocks lead to different worlds. Some arrangements place a continent at the equator beneath a humid belt. Others send it over a pole beneath ice. Some bring together landmasses to form continuous migration corridors. Others leave them isolated by shallow seas. Life evolves on whatever actual arrangement the planet happens to present at a given time. Our efforts to read that arrangement from the scars that remain remind us that the supercontinent cycle is both a real tectonic phenomenon and a reconstruction built from incomplete traces. Each new line of evidence narrows possibilities while often revealing fresh inconsistencies, keeping the story in motion and leaving open questions about how many supercontinents have truly existed and how exactly they have shaped the environment for life. The oldest surviving pieces of continental crust lie scattered across the globe as isolated blocks known as cratons. Each craton is a region where very ancient rocks have remained relatively stable, while younger belts of deformed crust and sediment have grown around them. Large cratons underlie much of central Canada, Western Australia, and southern Africa, and smaller ones appear in Greenland, India, Brazil, and elsewhere. Many of these cores contain rocks more than 3 billion years old. Within them, geologists find volcanic sequences, intrusive bodies, and sediments that preserve traces of early tectonic processes. When these fragments are examined in detail, a question arises that is difficult to answer with confidence. Did these ancient blocks once form a single early supercontinent, or were they part of several smaller continents that were only later gathered together? The evidence is incomplete and does not point in a single direction. In southern Africa, the Kapval Craton holds thick piles of volcanic and sedimentary rocks from the Archean Eon. In Western Australia, the Pilbara Craton preserves greenstone belts and granitic complexes of similar age. These two cratons show comparable volcanic histories and ages of crustal formation over a long interval from roughly 3.5 to 2.5 billion years ago. Some researchers note that their rock sequences match not only in age, but also in style, suggesting a related tectonic environment. On this basis, they propose that Kapval and Pilbara were once joined as parts of a larger entity, given the name Valbara. In this reconstruction, Valbara exists as a coherent continent for several 100 million years before being disrupted. The idea of Valbara is attractive because it assembles scattered evidence into a picture of a stable ancient landmass. However, the supporting data are patchy. Paleomagnetic measurements from rocks of that age are scarce and often altered, making it difficult to determine the relative positions and orientations of the cratons with precision. Some layers that were once thought to be direct matches turn out under closer scrutiny to differ in subtle but important ways. As more isotopic and structural information accumulates, the overlapping histories can be interpreted as arising either from shared origin in a single landmass or from similar processes operating in separate regions on a hotter early Earth. The proposed supercontinent remains a plausible but not universally accepted model. Other cratons add further complexity. In Canada, the Superior Craton preserves extensive volcanic arcs and sedimentary basins, that record a long period of crustal growth between about 2,700,000,000 and 2,400,000,000 years ago. In the same general time frame, parts of what are now northern Canada and Arctic Russia contain the Slave and other cratons with their own sequences of volcanic and plutonic rocks. Some studies group these cratons into larger ancient continents named Superia and Slavia that may have drifted and collided with each other. In some reconstructions, they are then gathered along with Cap Valpilbara and other blocks into an even broader structure called Kenneland toward the end of the Archean. This putative supercontinent would have combined many of the major Archean cratons into a single landmass. If it existed, its assembly would coincide with a marked cluster in Zircon ages and with widespread signs of crustal thickening and high-grade metamorphism. Yet here again the paleomagnetic record is muted, and the available data can often be fit by more than one configuration. One model places several cratons side by side in a roughly equatorial band. Another arranges them in a different pattern, closer to polar latitudes. In addition, later collisions and rifting events have overprinted structures in many of these regions, obscuring early sutures and reorganizing belts. It becomes difficult to tell which present-day boundaries correspond to Archean plate margins and which are products of younger tectonics. Some geologists respond to this uncertainty by favoring more conservative models. Instead of invoking a single large supercontinent, they see the late Archean as a time when several medium-sized continents existed moving on a convecting mantle and colliding in stages. In this view, the apparent synchrony in Zircon ages and metamorphic events reflects a planet-wide shift in tectonic style and heat flow, but not necessarily a complete gathering of all land into one piece. Others maintain that despite the uncertainties, the simplest unifying explanation of the data is that many cratons did in fact cluster in one or two major assemblies, even if the exact outlines cannot yet be drawn. A more speculative idea pushes the unification further back. Some reconstructions suggest that the oldest known cratons, when traced through time using their ages and geochemical signatures, cluster together at later times as parts of shared continents. If those clusters later reassemble, the suggestion is that all of the very ancient crust may once have formed in proximity, perhaps in a single early continent called Ur. In this scenario, UR emerges slightly after the first formation of continental crust, and persists in some form for a large part of Earth history, later merging with other land masses or being partly broken apart. Because the direct rock record from that early interval is sparse, these models are difficult to test. The notion of a single first continent, while appealing, rests on indirect patterns rather than on robust maps. All these competing pictures share a common difficulty. The evidence becomes thinner and more altered the further back in time one looks. In many Archean terrains, rocks have been metamorphosed multiple times. Original minerals are replaced, structures are folded and refolded, and chemical systems are overprinted. Some zircon grains retain their early ages, but their host rocks may now be high-grade gneisses that bear little resemblance to their initial sediments or volcanic units. Radiometric ages give reliable timings of crystallization events, but not always the spatial relationships that once existed between far-flung cratons. Without clear paleomagnetic poles from many regions and ages, the paths of early blocks over the surface cannot be tracked in detail. As a result, ancient maps remain sketch-like, with only the positions of a few key points marked and wide areas left blank. The physical and thermal state of the planet at the time adds another layer of uncertainty. During the Archean, the mantle is thought to have been hotter than today by several hundred degrees. Higher temperatures would influence how easily plates could form and how they moved. Some models suggest that early Earth may have hosted thinner, weaker plates, with more frequent overturn and perhaps smaller convection cells. In such a regime, plate boundaries might have shifted rapidly, promoting the creation of many small protocontinents that later coalesced. Other work argues that even on a hotter Earth, large plates could exist, and long-lived subduction zones might already have built significant continents. The amount of water in the mantle and crust at that time, the rate of heat production by radioactive decay, and the efficiency of heat loss through the surface all affect which picture is more likely. Direct constraints on these parameters are limited. For the history of life, the arrangement of early continents matters because it affects weathering, nutrient delivery, and the chemistry of oceans. Life in the Archean is microbial and largely confined to the seas and perhaps to shallow coastal environments. Continents, even if largely barren of plants and animals, present fresh rock to rain and river. The breakdown of minerals on land delivers ions such as calcium, magnesium, phosphorus, and silica to the oceans, where they influence the growth of microbial mats and the eventual precipitation of sediments. If most ancient crust was gathered into a single large continent, the distribution of river shorelines and shallow seas would differ markedly from a world with many smaller continents scattered around the globe. That difference would in turn affect where microbial communities could grow and how efficiently gases like carbon dioxide were removed from the atmosphere. However, because the fossil record from this time is sparse and often ambiguous, it is difficult to link specific biological changes to specific tectonic events. Instead, geologists and geobiologists must work with broad correlations. They note, for example, that the stabilization of several large cratons and the possible assembly of early continents coincide with changes in the composition of certain sedimentary rocks, and with hints of shifts in atmospheric chemistry. These associations suggest that the emergence of stable landmasses may have played a role in regulating climate and in setting environmental conditions for later evolutionary steps. The ambiguity in early reconstructions is therefore not only a technical challenge but also a scientific opportunity. Different plausible arrangements of Archean continents lead to different global climates, circulation patterns, and ocean chemistries in models. By comparing these scenarios with what little is known from ancient sediments and isotopic ratios, researchers can test which combinations of tectonic and climatic histories are consistent with the chemical and biological signals preserved. In this sense, the ghosts of the first superlands are not just missing pieces in a puzzle. They are variables in a set of experiments in which Earth itself is the subject and the outcome is the emergence of conditions suitable for complex life. As new methods refine the ages of old rocks, as trace elements in zircons and other minerals reveal more about their sources, and as paleomagnetic techniques push further back in time, some of the possibilities will be narrowed. It may become clearer whether early Earth was dominated by one long-lived continent, by a sequence of separate assemblies, or by a constantly shifting mosaic. For now, the first supercontinents, whether named Ur, Valbara, Kenorland, or by other terms, remain partly hypothetical structures grounded in real measurements, yet extending into uncertainty. Their outlines are drawn with dashed lines on maps signaling that something substantial likely stood in those positions, but that its exact form and influence are still open questions. By the middle part of Earth history, the scattered and partly speculative early continents give way to assemblies that can be traced with greater confidence. The rock record is richer, paleomagnetic poles are more reliable, and fossils begin to appear in abundance. Out of this clearer archive, several large landmasses stand out as major gatherings of continental crust. They are often called supercontinents, though even here definitions vary. Some researchers reserve the term for times when almost all continental area is united in one body. Others apply it more loosely to great clusters that nevertheless leave a few fragments adrift. Whatever the threshold, the sequence that emerges includes landmasses commonly referred to as Columbia, Rodinia, Pannosia, Gondwana, and Pangaea, each assembled from pieces of its predecessors, and each later broken apart. Columbia is often placed near the start of this better charted sequence. It is thought to have formed roughly between 2 billion and 1,500 million years ago by the collision and suturing of several older cratons, including those that now underlie North America, Greenland, parts of Western Europe, and perhaps fragments of Siberia, India, and Australia. Geological belts that record mountain building during this interval appear on multiple continents and can be matched across ocean gaps. They show consistent ages of deformation and magmatism, and in some cases align well when continents are repositioned using paleomagnetic constraints. When these belts are drawn together on a reconstruction, a large landmass emerges stretching perhaps from near the equator into higher latitudes. Around its margins, arcs and accretionary wedges record ongoing subduction and the attachment of smaller fragments. The interior, in contrast, appears to have been relatively stable for a long span of time. One feature associated with Columbia and its aftermath is a long interval sometimes referred to informally as the boring billion. Between about 1,800,000,000 and 800 million years ago, the geological record in many regions shows fewer signs of dramatic change than at other times. Major orogenies occur, but there is also extended stability in many sedimentary basins. The chemical composition of seawater inferred from certain isotopic ratios in marine sediments appears comparatively steady over long intervals. Life at this time is largely microbial, with eukaryotic cells evolving and diversifying slowly. In this context, a large long-lived supercontinent would influence weathering rates, ocean circulation, and nutrient supply in a way that could help maintain relatively stable conditions. Yet there is debate over how uniform this stability really was, and over how thoroughly Columbia united the continental crust. Some reconstructions suggest that several marginal blocks remained separate, reducing the degree of global assembly. Others argue that Columbia itself may have evolved gradually from earlier groupings, making its exact start and end difficult to define. The idea of a long quiet interval is anchored in several data sets but still open to refinement. As Columbia eventually breaks apart or reorganizes its constituent pieces, move into new configurations and participate in the assembly of another major landmass, Rodinia. Rodinia is generally placed as forming between about 1 billion and 800 million years ago. It is usually shown with the core craton of Laurentia, which later becomes much of North America at its center. Around Laurentia cluster parts of South America, Baltica, Amazonia, West Africa, Australia, Antarctica, and perhaps several Chinese and Siberian blocks. The positions of these surrounding continents remain uncertain. Some models place Australia and East Antarctica against the present western side of Laurentia. Others arrange them differently, perhaps along what is now the southern margin. Chinese blocks may lie either close to the northern edge or further away. These variations arise because different data sets, including paleomagnetism, matching of orogenic belts and sediment provenance, can be combined in more than one consistent way. Despite this uncertainty in detail, there is broad agreement that Rodinia represented a substantial gathering of continental crust. As Rodinia sat on the globe, its presence would have shaped climate. If large portions lay near the equator, enhanced weathering of warm, wet continental surfaces could have drawn down atmospheric carbon dioxide and influenced temperature. If instead large areas extended into high latitudes, their reflective surfaces could have promoted cooling. Some models of Neoproterozoic climate link the breakup of Rodinia to extreme glaciations, sometimes described as snowball Earth events, when ice sheets may have reached low latitudes. In these scenarios, rifting of the supercontinent creates new passive margins and shallow seas, altering ocean circulation and nutrient supply. Increased weathering of newly exposed rocks might further pull down greenhouse gases. The timing and severity of such glaciations and their precise connection to Rodinia's configuration remain matters of active study, but the coincidence in time points to a strong coupling between continental assembly and global climate states. Toward the end of the Neoproterozoic, Rodinia gives way to a more transient arrangement often called Pannotia. In some reconstructions, as Rodinia rifts apart, several of its blocks rotate and collide, again forming a new but short-lived cluster. In this view, parts of present-day Africa, South America and Laurentia come together near the South Pole, creating a continent shaped somewhat like a curved arc around a central ocean. Other models see Pannotia as less clearly distinct, more a stage in the progressive rearrangement of land rather than a fully separate supercontinent. The available evidence, though improved over the Archean, is still fragmentary, and the short duration of this configuration, perhaps on the order of 50 to 100 million years, leaves fewer chances for thick sediment piles and long-lived orogenic belts to form. At the same time, this late Neoproterozoic to early Paleozoic interval coincides with major shifts in the history of life. Fossils record the first widespread appearance of large soft-bodied organisms, followed by the more abrupt diversification of skeleton-bearing animals in the early Cambrian. Changing ocean chemistry, including an increase in oxygen levels, likely plays a key role. The interplay between tectonics, climate, and life becomes more apparent even if the exact causal chains remain debated. As the Neoproterozoic yields to the Paleozoic era, a new great continent, Gondwana, assembles. Gondwana is made up largely of land that will later become Africa, South America, Antarctica, Australia, India, Arabia, and smaller adjoining blocks. It forms through a series of collisions and suturing events that weld together previously separate cratons. Orogenic belts, such as the East African and Antarctic origins, mark the joins, preserving high-grade metamorphic rocks and magmatic arcs that testify to intense activity. By the early Paleozoic, Gondwana stretches from polar to tropical latitudes, occupying a vast area, especially in the southern hemisphere. Unlike the more speculative Pannotia, Gondwana is well documented. Its margins host thick sequences of marine sediments full of early animal fossils. Its interior holds glacial deposits that attest to large ice sheets at certain times, extending even into lower paleolatitudes in some reconstructions. Its assembly coincides with major reorganizations of sea level and with the rising and falling of shallow epicontinental seas that cover portions of the continent. These seas provide habitats for rapidly diversifying marine life. As Gondwana drifts, other land masses evolve around it. Laurentia Baltica and Siberia wander separately for a time, each with its own faunal provinces. Eventually, during the late Paleozoic, these northern continents and Gondwana converge to form perhaps the best-known supercontinent, Pangaea. The process is complex and unfolds over many tens of millions of years. Laurentia and Baltica collide to form Euramerica. Island arcs and smaller terrains accrete to their margins. Later, this combined northern landmass moves toward Gondwana. Between them lie ocean basins whose floors record subduction, while their margins experience volcanism and deformation. As convergence continues, those oceans close. The collision between Gondwana and Euramerica builds extensive mountain ranges, including the precursors of the Appalachians in eastern North America and related belts in Europe and North Africa. Further east collisions involving Siberia and smaller Asian blocks complete the assembly. By roughly the late Carboniferous to early Permian periods, most of Earth's land is gathered into one continuous body, or at least into a tightly knit cluster. Pangaea stretches almost from pole to pole and spans a large range of longitudes. The existence and broad outline of Pangaea are well supported. The fit of present-day continents around the North Atlantic and Western Tethys regions is close. Fossil assemblages, including those of land plants and vertebrates, show consistent distributions across areas that would have been contiguous on Pangaea, but are now separated. Paleomagnetic data indicate that the different continental blocks shared coherent paths relative to the magnetic poles. Together, these lines of evidence provide confidence in the general map, even if details of precise coastlines and internal basins remain uncertain. Pangaea's climate is strongly influenced by its supercontinental nature. The interiors of the landmass, far from the moderating influence of oceans, experience strong seasonal temperature contrasts and are thought to have been arid. Extensive desert deposits, including red beds and dune sandstones, attest to dry conditions in large regions. Along the coasts and near mountain ranges, monsoon-like circulation patterns likely produce strong seasonal rains. Coal deposits from lush forests occur in some belts where moisture is sufficient. Ice sheets occupy high-latitude portions of Gondwana during certain intervals, leaving behind glacial deposits and distinctive erosional features. The assembly of Pangaea is also associated with internal processes within the planet. As continents merge, they may act as a thermal blanket over the mantle, slowing heat loss beneath them. Over time, this can lead to the build-up of hotter buoyant mantle regions that rise and weaken the lithosphere. When this happens, rifting may begin, eventually splitting the supercontinent and leading to the formation of new ocean basins. In the case of Pangaea, signs of such processes appear toward the end of its existence. Large igneous provinces where enormous volumes of basaltic magma erupt in relatively short geological times accompany some stages of breakup. The Central Atlantic Magmatic Province, for example, coincides with the initial rifting between North America, South America, and Africa. Such events inject large amounts of volcanic gas into the atmosphere and may be linked to environmental stresses and biotic crises. The temporal association between the Central Atlantic Magmatic Province and a major extinction event at the Triassic-Jurassic boundary suggests a connection, though the exact mechanisms and their global effects are still under study. The pattern that emerges from these cases is that supercontinents are not static endpoints, but phases in a larger tectonic cycle. They assemble by accretion and collision influence climate and life during their tenure, and then break apart, often accompanied by episodes of intense magmatism. The intervals between their main phases of assembly fall in a broad range of hundreds of millions of years. This spacing, together with numerical models of mantle convection, suggests that there may be preferred scales and timescales at which the mantle organizes large-scale flow. Rising and sinking regions in the mantle might tend to arrange themselves in patterns that favor the periodic gathering and dispersal of continents. At the same time, the cycle is not strictly regular. The durations of assembly stability and breakup differ among Columbia, Rodinia, Gondwana, and Pangaea. Some landmasses, such as Gondwana, can be counted as supercontinents under looser definitions while still leaving substantial crust elsewhere. Others, like Pannotia, may exist only as brief and partly overlapping configurations. This irregularity raises questions about how strong the deep planetary rhythm really is. Are supercontinents inevitable products of internal convection, or do they depend sensitively on initial conditions and on the contingent outcomes of past collisions and rifts? The present record cannot yet discriminate fully between these possibilities. It does, however, make clear that Earth has passed through several radically different surface states, each with its own geography, climate patterns, and opportunities for life. The ages of gathering worlds are therefore not just chapters in tectonic history. They are stages in an ongoing experiment in which the same basic ingredients, continents and oceans, are mixed and arranged, repeatedly producing new boundary conditions for evolution each time the land comes together or drifts apart. As continents gather and separate, life responds not only at their margins, but also deep within their interiors where climate and geography combine in distinctive ways. On a planet with many medium-sized continents, distributed widely, ocean air can reach far inland. Coastal climates extend and corridors of suitable habitat connect distant regions. When a supercontinent forms, that pattern changes. The land interior becomes remote from the sea. The thermal inertia of the oceans no longer moderates seasonal changes there, and moisture has farther to travel. Early in the study of climate, Alexander von Humboldt measures temperature and pressure across Europe and parts of Russia, and notices that inland areas experience more extreme seasonal ranges than coastal ones at similar latitudes. Later observations extend this principle worldwide. Where land extends far from the sea, winters are colder summers, hotter, and the annual cycle more pronounced. This effect, called continentality, appears modest when applied to present-day Eurasia or North America. When trying to imagine a supercontinent, the same principle scales up. In the center of Pangaea, summer heat and winter cold likely exceed anything known on modern landmasses at similar latitudes simply because the distance to the oceans is greater. Rainfall patterns also shift. Moisture evaporates from the oceans and moves inland with winds, but mountain ranges stand in the way. As air masses are forced up over high terrain, they cool and release rain or snow. The air descending on the other side is drier, leaving a rain shadow where arid conditions prevail. On a supercontinent formed by multiple collisions, mountain ranges are abundant. Each collision between buoyant land masses produces an origin, and over time these chains stitch the interior together. The result is a complex topography of high plateaus and ridges, each casting its own climatic shadow. Sedimentary deposits from the late Paleozoic and early Mesozoic, when Pangaea exists, reveal widespread desert sandstones in regions that today lie in parts of North America, North Africa, and the Middle East. Fossilized dunes and wind ripples record the persistent action of dry winds across open sandy surfaces. Red beds stained by iron oxides indicate oxidizing conditions in soils and ephemeral river systems. Together, these lines of evidence support the idea that large parts of the Pangaean interior are semi-arid to arid for extended periods. Yet even in such a world, life finds niches. Along coasts and around inland seas, moisture is more abundant. In low-lying basins where rivers converge, floodplains form. Coal deposits from these regions preserve remains of dense forests including scale trees, seed ferns and early conifers. Amphibians and early reptiles inhabit swamp margins. The same supercontinent that hosts vast deserts also supports lush belts of vegetation where conditions allow. This contrast between harsh interior and more hospitable margins creates strong gradients in environment. For terrestrial organisms, these gradients shape distributions and evolutionary paths. During the Carboniferous and Permian periods, when Pangaea is assembling and then stands largely intact, large herbivorous and carnivorous tetrapods spread across connected land. Fossils of similar reptile groups appear in rocks of comparable age on what are now South America, Africa, India, and Antarctica. Their wide distribution is easier to understand if these regions are joined, allowing animals to move overland. Plant fossils likewise show repeated patterns across Gondwanan fragments, tying their communities together under shared climates. In marine realms, supercontinents influence life differently. The arrangement of land affects ocean basins, currents, and nutrient upwelling. When continents cluster, a single world ocean may surround them with only limited marginal seas. The circulation in such an ocean could be less complex than in a world with multiple separated basins. Nutrient delivery from rivers concentrates along continental margins where upwelling and currents can stimulate productivity. Interior shelves of a supercontinent may host broad, shallow seas when sea level is high, providing extensive habitats for marine life. During times when Pangaea exists, certain marine faunas become cosmopolitan, spreading widely around the supercontinental margins. Others remain restricted to particular basins or climatic zones, forming distinct biogeographic provinces. The fossil record shows both patterns, and their interplay reflects the balance between connectivity and environmental variation. Over longer spans of geological time, the assembly and breakup of supercontinents appear to coincide with major events in the history of life. The Cambrian explosion of animal diversity follows not long after the breakup of earlier Neoproterozoic configurations, when rifting creates new continental margins and shallow seas. Later, the assembly of Pangaea is accompanied by shifts in terrestrial floras and faunas as lineages spread across joined lands and new environments appear in the interior. The end-Permian mass extinction, one of the most severe known, occurs near the transition from a fully assembled Pangaea to early stages of breakup. This event eliminates a large fraction of marine species and significantly reshapes terrestrial ecosystems. Some models suggest that the supercontinental configuration contributes to environmental stresses including extreme climates, low oxygen levels in parts of the ocean, and changes in nutrient cycles. The eruption of a large igneous province in what is now Siberia around the same time releases massive amounts of volcanic gas, further perturbing climate and ocean chemistry. It is difficult to disentangle cause and effect. The coincidence of supercontinent tenure, large-scale volcanism, and biotic crisis hints at a coupled system in which tectonics, mantle dynamics, and life interact. However, supercontinents do not always align neatly with extinctions. Some periods of biological diversification occur while large continents are intact. Others take place in the wake of rifting and new basin formation. Analyses of diversity through time have sometimes suggested long-term cycles or pulses on the order of tens of millions of years that might be linked to tectonic rhythms. These proposals remain debated, with some researchers emphasizing the influence of sampling biases in the fossil record and others pointing to correlations with sea level change, continental flooding, and the creation of new habitats along rifted margins. The question of whether there is a strong regular signal of the supercontinent cycle in biodiversity patterns remains open. Genetic studies add new dimensions. As methods for comparing genetic material across species improve, phylogenetic trees can be dated at least approximately using molecular clocks calibrated by fossils. For some groups, such as certain plants and vertebrates, divergences between major lineages seem to coincide with times when continents separate or collide. For example, the split between lineages confined to northern and southern landmasses sometimes aligns with the breakup of Pangaea into Laurasia in the north and a reorganized Gondwana in the south. In other cases, divergences occur long after physical separation, indicating that species remained connected through land bridges or island chains, or that speciation was driven by ecological rather than purely geographic isolation. These nuances remind that continents and oceans set broad boundary conditions, but local environments and biological traits determine how organisms respond. One recurring pattern is that of refugia and expansion. As supercontinents form, some regions become barriers such as wide deserts or high mountain ranges, while others serve as corridors such as river valleys and coastal plains. During climatic shifts, including glacial advances and retreats, populations may contract into favourable pockets, survive there and later expand when conditions improve. Over repeated cycles, this dynamic can generate complex distributions and hidden genetic structure. On Pangaea, such refugia might lie along moist coasts or in mid-latitude basins sheltered by topography. In earlier supercontinents, they would take different specific forms but follow similar principles. The breakup of supercontinents introduces a different set of opportunities. As rifts open and new shorelines form, previously continuous populations are split. Isolated on new continents, they follow independent evolutionary paths. The classic example is the divergence of lineages on the southern continents after the fragmentation of Gondwana visible today in the distributions of marsupials, retite birds, and many plant groups. Although not all such patterns derive solely from Gondwanan breakup, there is a clear imprint of ancient connections. On a longer view, supercontinents can be seen as both consolidating and resetting elements of the tree of life. During assembly, lineages that were once separate can mix, compete, and hybridize. During tenure, unique combinations of climate and geography allow new adaptive zones to be explored, especially along coasts and in varied topographies. During breakup, isolation and environmental change drive bursts of speciation. The net effect is not a simple periodic forcing of diversity up or down, but a sequence of reorganizations at many scales. The interior deserts of Pangaea, for example, may limit diversity in some groups that require moist conditions, while at the same time selecting for traits in other groups that can tolerate aridity, leading to new desert-adapted forms. The repeated creation of similar environments in different eras, such as inland plateaus or monsoonal coasts, also raises a subtle question. If comparable physical settings recur whenever continents form certain configurations, do similar biological solutions reappear? Fossil floras and faunas suggest that convergent evolution is common. Desert communities in different periods on different continents often show analogous structures with small drought-tolerant plants and burrowing animals. Mountain ecosystems evolve distinct high-altitude specialists each time new ranges rise. In this sense, while the exact species are different, the broad outlines of ecosystems echo through time as supercontinents assemble and decay. The study of life on supercontinents is therefore not just a cataloguing of which animals live where. It is an attempt to see how deep time geography constrains and channels evolution, how repeated patterns of joining and splitting influence the spread, isolation, and adaptation of lineages. Many details remain unclear. For several supercontinents, the positions of landmasses, the strength of climate gradients, and the distributions of habitats are still under refinement. Fossil records are uneven, richer in some regions and intervals than others. Genetic clocks carry uncertainties in their calibration. Nevertheless, the broad picture is one in which the architecture of the solid Earth sets a moving stage that repeatedly rearranges the possibilities for life. Supercontinents, with their vast interiors and extended margins, are among the most dramatic forms that stage can take. On a planet covered by a single vast continent, the basic physics of air and water continue as they do today, but the scale and arrangement of land change the outcome. Solar radiation still heats the tropics more than the poles. Warm air still rises and moves poleward, and cool air sinks and returns. oceans still store and transport heat. Yet when almost all the land is gathered into one block far from some coasts, and ringed by others, the circulation of atmosphere and ocean adjusts in ways that push climates toward extremes. Models of supercontinent climates use the equations of fluid dynamics and radiation, solved on grids that wrap around a globe. When researchers feed these models with reconstructions of past continental positions and estimates of greenhouse gas levels, the simulations reveal patterns consistent with what the geological record suggests. Over the broad interior of a supercontinent, summers become very hot. Land surfaces dry quickly under strong sunlight, and without nearby oceans to moderate the temperature, heat builds through the season. In winter, those same interiors cool rapidly. Long nights and clear skies allow infrared radiation to escape into space. With little moisture and cloud cover to trap heat, temperatures drop well below those of present-day continental mid-latitudes at the same distance from the equator. This combination of hot summers and cold winters is the amplified continentality already hinted at by Humboldt's 19th century measurements extended to a global scale. Precipitation in such interiors is limited. Moist air from the ocean loses much of its water as it is forced over coastal mountains and intervening ranges. By the time air masses reach the central plateau of a supercontinent like Pangaea, they are dry. Models show belts of subsiding air in these regions which inhibit cloud formation and rainfall. The geological record supports this picture. Thick sequences of wind-blown sand with fossilized dunes showing consistent orientations point to persistent dry winds and arid conditions. Evaporate deposits made of minerals that precipitate as enclosed basins dry out. Further, confirm that water bodies in the interior often shrink and leave concentrated salts behind. At the same time, along the margins of the supercontinent, a different regime operates. Sea breezes bring moisture inland. When the land heats strongly in summer, pressure differences between land and ocean intensify, driving powerful monsoon systems. Warm, moist air sweeps in from the surrounding ocean, rises over hot coastal plains and mountain slopes, and releases heavy seasonal rains. In some regions, model results show a strong annual cycle, prolonged dry seasons followed by brief but intense wet seasons. Sedimentary records from ancient deltaic and fluvial systems support the idea of seasonal flooding. Alternating layers of coarse and fine sediments, paleosols that indicate repeated wetting and drying, and plant fossils adapted to variable water availability all point toward monsoon-influenced climates along certain Pangaean coasts. The juxtaposition of dry interior and wet margins creates sharp climatic gradients. These gradients affect vegetation patterns, soil development and erosion. Where rainfall is abundant but seasonal rivers carry large sediment loads from uplands to lowland basins, building broad alluvial plains and deltas. These regions can be highly productive, supporting dense plant cover when water is available. When the rains fail or weaken, drought extends inland. Dust then becomes a prominent feature. In dry central regions, strong winds mobilize fine particles from exposed soils and deflated basins. This dust can be carried thousands of kilometers, crossing belts of latitude and depositing in distant areas, including coastal oceans. Modern analogues occur today when dust from the Sahara crosses the Atlantic and fertilizes parts of the Amazon basin and the Caribbean. In a supercontinental setting, such fluxes may be larger and more persistent. Layers of fine-grained sediments found in offshore sections, sometimes bearing chemical signs of continental origin, have been interpreted as products of past dust transport. These fluxes matter because they transfer iron and other micronutrients to the ocean surface where they can influence phytoplankton growth and by extension the global carbon cycle. High plateaus formed during continental collisions add further complexity. When continents collide, crust thickens and uplifts, creating elevated regions, possibly several kilometers above sea level. Today, the Tibetan Plateau plays an important role in shaping Asian climate. It acts as a heat source in summer, reinforcing the South Asian monsoon by warming the overlying air and enhancing rising motion. It also influences the jet stream and storm tracks. In a supercontinent, the combined effect of multiple plateaus and ranges could be even more pronounced. Models that include large elevated interiors show strong stationary waves in the atmosphere, steering westerly winds, guiding storm systems, and concentrating rainfall in particular zones. These patterns in turn affect where glaciers can form at high elevations, where rivers carve deep canyons, and where conditions might be suitable for particular ecosystems. Evidence from ancient glacial deposits supports the notion that even within generally warm supercontinental climates, high topography can host ice. Striated bedrock dropstones in marine sediments and characteristic unsorted debris deposits show that during certain intervals glaciers and ice caps existed on highlands within Gondwana and possibly within earlier landmasses. These ice bodies would have stored water and altered local albedo, creating feedbacks on regional climate. In cold periods, expansion of ice across plateau surfaces increases reflectivity, encouraging further cooling locally. When climates warm, ice retreats, exposing darker rock or soil that absorbs more sunlight, reinforcing warming. The response of the global climate system to changing supercontinent configurations is not limited to the atmosphere. Ocean circulation also reorganizes. The shape and position of continents determine the pathways available to currents. When land encircles the poles or isolates basins, currents can be blocked or redirected. In present times, the Antarctic circumpolar current flows unimpeded around Antarctica, significantly isolating the continent and contributing to its cold conditions. In some past supercontinent states, similar circumpolar currents may or may not have been possible depending on where coastlines lay. When Pangaea existed, a large world ocean, sometimes called Panthalassa, surrounded most of the land, while a smaller but significant ocean, often referred to as the Paleotethys, and later Tethys, lay between Gondwana and northern terrains. The connections between these basins and the presence or absence of seaways at certain latitudes would have controlled the movement of warm and cold water masses. Deep water formation driven by cooling and increased salinity at the surface might have been concentrated in particular zones, and the resulting overturn could have been slower or more restricted than in a world with multiple connected oceans. Sediments rich in organic carbon laid down in oxygen, poor deep waters, and patterns of certain isotope ratios in marine rocks give clues to these ancient circulation modes. Times when parts of the ocean became stagnant or oxygen depleted often coincide with black shale deposition and with stresses on marine life. Some of these intervals appear during supercontinent tenure or during their breakup, pointing to a link between geography circulation and ocean chemistry. Such links highlight how a joined world might stress the concept of habitability. For complex life, stable access to liquid water, moderate temperatures and sufficient oxygen are important. Supercontinents tend to encourage extreme conditions in some regions and to alter the distribution of productive marine areas. In the interior deserts, temperatures and aridity may exceed what many plant and animal groups can tolerate. Along some coasts, strong monsoons can produce floods, storms, and variable conditions. In certain basins, low oxygen bottom waters and high nutrient inputs could favor blooms of specific organisms, perhaps including those that produce toxins. At the same time, other regions may remain relatively benign with temperate climates and steady rainfall. The question is not whether a supercontinent makes Earth uninhabitable, but how much of the surface remains within comfortable limits for different forms of life, and how those habitable zones shift over time. Comparisons between geological evidence and climate models provide partial answers. For Pangaea, plant fossils from many latitude bands show that forests exist from equatorial to high latitudes, though their composition changes. Growth rings in fossil wood indicate varying seasonality. Some trees record rapid growth during short wet seasons and slow growth during extended dry periods consistent with monsoon cycles. Animal fossils reveal that diverse vertebrate communities occupy both low latitudes and higher ones with adaptations suited to local conditions. Insects, early reptiles and synapsids exploit different niches in river valleys, uplands and coastal plains. These records suggest that despite harsh regions, large areas of the supercontinent remained supportive of complex ecosystems over tens of millions of years. The emerging picture is that supercontinental climates are structured and varied rather than uniformly hostile. However, they may be more sensitive to external and internal forcing. A change in greenhouse gas concentrations driven by volcanic eruptions or by shifts in weathering rates could push some regions across thresholds more quickly than in a world with more ocean-dominated mid-latitudes. Feedbacks involving ice vegetation and dust might amplify or damp particular responses. For example, if warming dries interior soils, furthermore dust will be raised, potentially affecting radiation balance and cloud formation. If cooling allows snow cover to expand over large parts of the land, the increased reflectivity could feed back strongly on temperature. The range of possible climate states accessible to a supercontinent Earth might therefore be broader, with both very warm and very cold endpoints more easily reached under certain conditions. Extending this thinking beyond Earth, the concept of supercontinentality becomes relevant to the search for life on other planets. A rocky exoplanet in the habitable zone of its star might hold surface water and an atmosphere, but its habitability could be shaped by whether its land is broken into many continents or gathered into one or two. Without direct imaging, these details remain unknown for distant worlds. Yet by examining our own planet's behavior under different configurations, scientists can build a catalogue of possible climate regimes. If a planet shows signs of long-term climate stability that might hint at plate tectonics and balanced arrangements of land and sea, if instead it exhibits evidence of extreme swings, perhaps its continents have passed through states similar to our supercontinents. For now, these ideas remain speculative, but they are anchored in the same physics that govern Earth's atmosphere and oceans. In this way, the weather of a joined world is not just a chapter in Earth's history. It is a template for understanding how the arrangement of land can push a climate system toward or away from conditions that allow complex life. Each supercontinent that has existed on Earth provides another example of how far the system can be stretched, while still supporting a diverse biosphere. Future work combining improved reconstructions of past geography with refined climate models and more detailed sedimentary records will continue to test and sharpen this picture. The broad conclusion already clear is that supercontinents amplify contrast. They make some regions harsher and others more dynamic, and they ensure that any life that persists through such intervals must adapt to a world where the extremes of climate are written large across a single connected land. In the present day, instruments anchored to bedrock measure the slow motion of Earth's surface with high precision. Signals from navigation satellites reveal that continents are not fixed, but slide over the globe at rates of a few centimeters per year. Over a human lifetime, this movement is imperceptible, but over tens or hundreds of millions of years it reshapes oceans and land. Africa shifts northward toward Europe. Australia moves north toward Southeast Asia. The Atlantic Ocean widens along its central ridge. The Pacific, encircled by subduction zones, gradually shrinks as its floor is consumed at trenches. By combining present motions with geological records of past plate interactions, researchers attempt to project the future evolution of continents. These projections are not precise predictions, but scenarios each built on assumptions about how mantle convection patterns may persist or reorganize, and about where new subduction zones might initiate. Despite the uncertainties, several broad classes of future supercontinent have been proposed, each with distinct geography and climatic implications. One family of scenarios envisions a supercontinent sometimes called Pangaea Ultima. In this picture, the Atlantic does not continue to widen indefinitely. Instead, new zones of subduction form along its margins, especially off the eastern coasts of the Americas. Once subduction begins, oceanic crust in the Atlantic starts to sink back into the mantle. Spreading at the mid-ocean ridge slows and may eventually cease. Africa, which has already been moving toward Europe, closes the Mediterranean and collides fully with Eurasia, raising new mountain ranges where the present sea lies. The combined Afro-Eurasian landmass acts as a stationary or slowly drifting anchor. North and South America, drawn by the consumption of Atlantic crust, and by interactions at their western edges, migrate eastward. Over a timescale on the order of 200 to 300 million years, the Atlantic basin narrows and disappears. The Americas weld onto Africa and Europe, sealing the last vestiges of the ocean and forming a new continuous supercontinent, roughly centered near the former position of the equator. In some reconstructions, a large inland sea remains where parts of the former Atlantic persist in an enclosed basin. In such a world, the Pacific may be larger than today, or may have been partly replaced by new oceanic regions opened behind migrating plates. The details depend on how subduction boundaries propagate, and on the interplay between sinking slabs and rising plumes in the mantle. A second family of scenarios emphasizes the ongoing closure of the Pacific, while allowing the Atlantic to continue widening. In these models, sometimes grouped under the name Nova Pangaea, subduction remains dominant along the Pacific Rim. Oceanic lithosphere in the Pacific continues to be drawn downward at trenches around East Asia, Australasia, and the Americas. Over time, this process brings the margins of the surrounding continents closer together. North and South America drift further west relative to Eurasia and Australia, eventually colliding with East Asia in a broad belt. The Pacific basin narrows and may vanish, replaced by mountain belts and interior basins where ocean once lay. Meanwhile, the Atlantic grows wider between an amalgamated American-Asian landmass and a reorganized Afro-European one or fragments of these. The resulting supercontinent has a different outline from Pangaea, Ultima often illustrated as an elongated band of land encircling part of the globe with a large single ocean on the opposite side. In this configuration, the climatic consequences would differ. Coastal climates might dominate along the long, sinuous shoreline of the supercontinent, while interior regions, although still distant from the sea, in some places might be less centrally isolated than in a more compact Pangaea Ultima. A third type of scenario, commonly referred to as a major, situates the next supercontinent near the North Pole. In this case, the present trend of Northern Hemisphere plates drifting northward continues and intensifies. The Arctic Ocean closes as Eurasia, the Americas and smaller northern blocks converge. The Pacific and Atlantic basins change shape, but the key feature is that much of the continental mass ends up clustered around high northern latitudes. In some major reconstructions, Antarctica remains largely isolated in the south, perhaps connected to the main supercontinent by narrow land bridges or island arcs. In others, parts of Gondwanan fragments join the northern assembly along a long meridional band. The climatic signature of such a polar-centered supercontinent would be distinct. Large land areas at high latitude favor extensive ice sheets, provided greenhouse gas levels are not extremely high. The presence of a massive ice-covered plateau near the pole would influence planetary albedo atmospheric circulation and sea level. Glacial conditions might be more persistent than in equator-centered supercontinental states. However, because the models that generate a measure vary in the timing and exact path of plate motions, the extent of glaciation and the stability of such a configuration remain open to investigation. A further more speculative scenario proposed in some studies is named Orica. In this vision, both the Atlantic and the Pacific ultimately close, and a new ocean opens elsewhere, perhaps cutting across the interior of the present Pacific or along an entirely new rift. The continents then assemble into a configuration that does not strongly resemble either Pangaea or a simple mirror image of it. The driver in these models is the idea that subduction zones and mid-ocean ridges reorganize over very long timescales as dense slabs accumulate at the base of the mantle and hot upwellings emerge in new places. The exact geometry of future continents in such a case is highly uncertain, but the scenario illustrates that the variety of potential supercontinental arrangements is wide given the complex behavior of the mantle. Underlying all these possibilities is a question about the persistence of plate tectonics itself. Earth's interior cools over time as heat from formation and radioactive decay is gradually lost to space. As the mantle cools and convection slows, it may become harder to sustain the stresses needed to bend and break plates. Some models suggest that plate tectonics could eventually give way to a more stagnant lid regime somewhat akin to present Venus, but reached by a different path. If this transition happens before the next full supercontinent forms, the pattern of land and ocean might freeze in a partially assembled state. Alternatively, the cooling may be slow enough that several more supercontinent cycles occur before tectonic style changes. On top of these internal processes lies the evolution of the Sun. Over the next several 100 million years, solar luminosity is expected to increase gradually. This brightening will raise the amount of energy Earth receives, tending to warm the climate. Weathering of silicate rocks and the long-term carbon cycle may compensate to some degree by reducing atmospheric carbon dioxide, but at some point those feedbacks may not be sufficient to keep surface temperatures within the range comfortable for complex life. In many projections, sometime within the next 1 to 2 billion years, Earth's surface becomes hot enough that oceans begin to evaporate more rapidly, water vapor accumulates in the atmosphere, and a moist greenhouse state develops. If a new supercontinent forms within the shorter window of a few 100 million years, it will do so under a sun slightly brighter than today, with potentially lower carbon dioxide levels if weathering continues efficiently. The combination of supercontinentality and increased solar input could drive climates in directions different from those experienced by Pangaea or Gondwana. Interior deserts might become hotter, high-latitude regions might remain temperate without extensive ice. Monsoon systems might strengthen or weaken depending on the balance between land heating and atmospheric composition. The future biosphere, if it still includes complex multicellular life at that stage, would have to adjust to these conditions. Whether humans or their cultural descendants are present to witness a future supercontinent is unclear and lies outside the scope of geological projection. What can be said based on current understanding is that the physical processes that built and broke past supercontinents are still operating. Plates continue to move, subduction zones still consume ocean floor, and continents still collide along active mountain belts. The long-term endpoint is constrained by planetary cooling and stellar evolution, but within those bounds the system has room for several more large-scale rearrangements. From the perspective of life, each such rearrangement would again alter climate gradients, ocean currents, and the connectivity of habitats. New deserts and mountain chains would arise, new inland seas might open, and new coastal shelves would be flooded or exposed. Evolution would play out against a changing map as it has in the past, with lineages expanding, contracting, and branching in response to the new conditions. The different named scenarios for the next supercontinent serve as frameworks for thinking about these eventualities. Pangaea, Ultima Nova Pangaea, Amasia and Orica are not competing predictions so much as examples of how sensitive the outcome is to initial conditions and to the future development of plate boundaries. Small differences in where subduction initiates, in how quickly certain ridges slow or speed up, or in how mantle plumes interact with the lithosphere can lead to distinct continental futures. The geological record of past supercontinents, even with its gaps and ambiguities, offers a way to check which patterns recur and which are rare. It shows that supercontinents have formed several times already, that they have taken different shapes, and that they have influenced climate and life in multiple ways. It does not yet show a rigid periodicity or a single preferred geometry. In this sense, the next convergence is both expected and open-ended. The physics of convection and crustal strength make it likely that continents will eventually come together again in some form. The exact map of that future world and the details of its climate and biosphere remain unknown. From the standpoint of this narrative, the possibility of a future supercontinent closes a loop that began with an imagined lost land for lemurs and continued through the reconstruction of real ancient supercontinents. It brings the story back to the present, where the slowly shifting plates beneath modern continents carry the seeds of a new joined world whose outlines are only faintly visible in models. Whether that future world will host forests and animals, or only microbial communities adapted to warmer seas and drier lands, is tied to long-term trends that extend beyond tectonics alone. The certainty that plates will move and that continents will one day collide again is set against the uncertainty of how hospitable Earth will be when that happens. That tension between predictable deep processes and the open future of life gives added weight to the question of how supercontinents shape not only the past of Earth but its eventual fate. When scientists look beyond Earth to its neighbours and to planets around other stars, they carry with them the understanding that continents and supercontinents are not guaranteed features of a rocky world. The comparison begins close to home with Mars. Mars is smaller than Earth and has cooled more quickly. Spacecraft from NASA and other agencies have mapped its surface in detail, revealing vast volcanoes, deep canyons, impact basins, and ancient river valleys. However, the pattern of these features and the underlying gravity field suggest that Mars does not currently host plate tectonics in the sense that Earth does. Its outer shell appears relatively rigid and continuous. Volcanic provinces like Tharsis stand as broad swells, perhaps supported by long-lived mantle upwellings, but there is little sign of systematic spreading ridges and subduction zones forming global networks. Crustal thickness maps derived from gravity and topography show thickened regions and thinner ones, but not the kind of organized plate mosaic seen on Earth. At the same time, Mars preserves an ancient magnetic imprint in parts of its crust. Measurements from orbit show bands of magnetized rock in the southern highlands, where the orientation of the magnetic signal flips across parallel stripes. On Earth, similar patterns arise from seafloor spreading and magnetic field reversals. On Mars, the bands are less regular and occur in heavily cratered terrain. Their presence hints that early in Martian history there may have been processes that resembled plate tectonics, or at least organized mantle flow and crustal formation under an active global magnetic field. Later, as the planet cooled and its internal dynamo shut down, those processes may have slowed or ceased, leaving behind fossil traces in the crust. The seismic data from a lander that recorded Marsquakes add another piece. The waves travelling through the interior paint a picture of a thick lithosphere, overlying a mantle that is still convecting but perhaps less vigorous than Earth's. The absence of widespread young subduction features suggests that any mobile lid regime ended long ago. If Mars ever hosted something like continents, they did not grow and drift for billions of years as Earth's have. Without long-lived mobile continents, the Martian surface did not experience repeated supercontinent cycles. Its climate history, recorded in layered sediments and valley networks, reflects other controls, changes in orbital parameters, atmospheric loss to space, and the waxing and waning of polar caps. With a thinner atmosphere, lower gravity and greater distance from the Sun, Mars evolved into a cold, mostly dry world with only local and transient liquid water in later times. Whatever life, if any, arose, they would have faced a different set of constraints from those on Earth, where continents and oceans and their rearrangements have dominated environmental change on long timescales. Venus, already considered earlier, offers a different contrast. It shares Earth's size and likely its initial bulk composition, but its present stagnant lid tectonics and extreme greenhouse atmosphere show that similar starting conditions can diverge sharply. There is no clear evidence in current data that Venus ever passed through a sustained plate tectonic phase with drifting continents. Some models allow for episodes of limited subduction, or for early mobile lids before the planet heated and dried to its present state, but the radar record from missions like Magellan reveals a surface dominated by basaltic plains and deformation belts without clear analogues to Earth's ocean-continent mosaic. The lack of supercontinent cycles on Venus in its accessible history suggests that mobile continental plates are not an inevitable outcome even for Earth-like planets. Between Mars and Venus, Earth stands as the only example in the solar system of a rocky planet with large, buoyant continents that collide and break apart repeatedly. This uniqueness raises a question that extends beyond local geology. Are supercontinents a rare feature in the universe dependent on a narrow range of planetary properties, or are they a common result of certain combinations of mass, temperature, and water content? Earth's particular tectonic style likely depends on several factors coinciding. Its size is large enough to retain internal heat and drive convection for billions of years, but not so large that the lithosphere becomes too thick and heavy to break. Its water inventory, partly at the surface and partly within the mantle, weakens minerals and promotes brittle failure and subduction. Its internal heat production from radioactive elements and its cooling rate produce mantle convection cells of a scale comparable to continental dimensions. Its early history, including giant impacts and the formation of the Moon, may also have influenced the thickness and composition of its crust. These conditions may define a window for active plate tectonics. Planets significantly smaller than Earth might cool too quickly, freezing into stagnant lids after only brief episodes of mobility. Planets significantly larger might develop high-pressure mineral phases and strong lithospheres that resist subduction. Planets too dry might never lubricate plate boundaries, while those with very deep oceans and little exposed land might form only thin basaltic crust. In such cases, the equivalent of supercontinents would not arise, and the surface would evolve along paths more like Mars or Venus. Observationally direct tests of these ideas on exoplanets are not yet possible. Telescopes can measure the sizes and orbits of many planets around other stars, and in some cases can infer rough densities. For a few spectra of their atmospheres provide hints of composition. However, present instruments cannot map their surfaces or detect the presence of continents. In the future, techniques that look for variations in reflected light as a planet rotates may in some favourable cases reveal whether its surface has contrasting bright and dark regions, consistent with continents and oceans. The pattern of such variations over time could in principle suggest whether large landmasses exist, and whether they are clustered or dispersed. For now, such applications remain at an early stage. In parallel, researchers use computer models to explore how common Earth-like tectonics might be in a statistical sense. They vary planetary mass composition, water content, and interior temperature in simulations of mantle convection and lithospheric behavior. Some studies find that over a range of parameters near Earth's mobile plate regimes can arise, while for others a stagnant lid is more stable. The presence of surface water both as an agent of weathering and as a lubricant at plate interfaces often emerges as a key factor. This result connects the deep interior to surface conditions in a tight loop. If a planet has enough water to weaken its lithosphere and drive plate tectonics, it may also have oceans that regulate climate. If plate tectonics is active, it can help maintain long-term climate stability by recycling carbon. Stable climate in turn supports liquid water over long spans, closing a feedback that may be favourable for life. Supercontinents sit within this loop as visible products of a working plate system. Their assembly and breakup represent surface expressions of slowly shifting convection patterns deep in the mantle. In that sense, they can be thought of as part of a very slow rhythm in the coupled interior surface system, one that operates on timescales much longer than individual climate cycles or evolutionary radiations. The presence of a supercontinent or its absence at a given time gives a snapshot of the phase of that rhythm. Yet unlike a precise clock, the timing of supercontinent cycles appears irregular. Intervals between major assemblies change, configurations differ, and some stages may involve partial gatherings rather than complete unions. The underlying mantle flow is chaotic in detail, responding to variations in composition, heat sources, and boundary conditions. The concept of a planetary heartbeat in this context is more a guiding image than a strict description. It points to the idea that there are characteristic scales and tendencies in convection that favour certain patterns without enforcing exact periodicity. For the evolution of life, what matters is that this deep, slow motion continually reshapes the surface environment in ways that are neither entirely random nor completely predictable. Each supercontinent brings new distributions of land and sea, new climates, new migration pathways, and new barriers. Each breakup opens new edges where ocean and continent meet, creating fresh, shallow seas and coasts. These changes alter the setting for evolution, repeatedly offering opportunities and imposing constraints. On Earth, this repeated rearrangement has coincided with the rise of increasingly complex ecosystems, from microbial mats in shallow Archean seas to forests, insects, reptiles, birds, and mammals on later continents. It is tempting to ask whether something like this path would be likely on any planet with active plate tectonics and supercontinents. If continents gather and disperse elsewhere, might they similarly shape the pace and direction of biological innovation? Or is Earth's particular sequence of supercontinents and life events a singular outcome of many contingencies? These questions remain open because there is so far only one example to study in detail. Within that one example, patterns emerge. Certain kinds of climate states, such as extensive interior deserts and strong monsoons, recur when land masses cluster. Certain types of mountain ranges and basins form, again and again, as collisions and rifts repeat. Similar ecological niches appear each time comparable physical settings arise. At the same time, the particular lineages that fill those niches differ, and the timing of key transitions, such as the origin of land plants or the radiation of mammals, depends on many factors beyond tectonics alone. The emerging view is that supercontinents are neither mere background nor absolute drivers. They are structural features of Earth's long-term evolution that interact with climate chemistry and biology in complex ways. They set broad contexts within which more local processes operate. Looking back, the lost imagined continent of Lemuria gives a glimpse of how limited data and strong patterns in the distribution of life once led researchers to propose a vanished land bridge. Modern science has replaced that conjecture with the richer story of real supercontinents, traced through rocks, fossils and fields, and with a recognition that continents themselves move on a restless planet. Looking outward, the quiet basaltic plains of Venus and the cold highlands of Mars show that Earth's mode is not universal. Far beyond countless rocky planets orbit stars of many types, some perhaps with conditions that could support liquid water and atmospheres for long times. Whether any of those worlds carry drifting continents that sometimes join to form supercontinents is unknown. If they do, their biological histories, if any, may be deeply influenced by those cycles just as Earth's has been. If they do not, they may follow very different paths. In that uncertainty lies one of the central questions of planetary science and astrobiology. Are the great joined lands that have shaped Earth's climate and life a common feature of habitable worlds, or a rare outcome of a particular combination of size, composition, water, and history? The answer, when or if it is found, will tell not only how Earth fits into the wider family of planets, but also how much of its long story of supercontinents and life is shared by others, and how much is uniquely its own.